Okay, let's move on to section 3.3 of Anton, which is about orthogonality. And so recall that the dot product of two vectors u and v is equal to the norm of u times the norm of v times the cosine of the angle between them. Now, if theta, the angle between them, is 90 degrees, then cosine of 90 degrees is 0. And so the dot product becomes 0 because the cosine term is 0. And then conversely, if the dot product is 0 and u and v are non-zero vectors, then the angle between them has to be 90, because if the dot product is 0, that means the norm of u times the norm of v times the cosine of theta is 0. Since u and v are non-zero, that forces cosine of theta to be 0, and then that forces theta to be 90 degrees. And so the dot product can detect whether two vectors are orthogonal or perpendicular. Those two words are used interchangeably. Another word also used along with orthogonal and perpendicular is normal. So these two vectors, u and v, in Rn, are defined to be orthogonal or perpendicular if and only if their dot product equals 0. A simple example is that the standard basis vectors in any Rn are orthogonal, and that's simply because we take their dot product and it's equal to 0. Here's some specific examples of E1 and E2. The dot product is, well, 1 times 0 is 0, 0 times 1 is also 0, and all the other terms are 0. And so when you add it all up, you get 0, and so these vectors are orthogonal. And to picture in R3, E1, E2, and E3, well, here's how they are pictured. And you can see that E1 and E2 are perpendicular just because they're the vectors along the x and the y-axis. Okay, moving on to what we're going to do next is we can use the dot product to describe a couple things. One being the equation of a line in R2, and then the second being the equation of a plane in R3. So let's begin with the story of the equation of a line in R2. So here's R2, and here in magenta I've got a line. And suppose we have a point P0 on the line with its coordinates being some numbers x0 and y0. So for example, x0 might be 2, y0 might be -1, and so this point here would have coordinates 2, -1, or what have you. And then let's also assume we have what's called a normal vector, or sometimes called perpendicular. And this is a vector that when you draw it, it's perpendicular or orthogonal to the line. And if we draw the vector starting at the origin, it'll end at some number AB. So that's how we identify a vector with a pair of, well, in R2, a pair of numbers. And then any point on this line, an arbitrary point x comma y, it has to satisfy that when you take the dot product of the normal vector, that's in green here, and the vector that is going from P0 to P, it's an arrow starting at P0 and ending at P, that those two vectors, their dot product has to be 0. That's essentially by the definition of normal vector being normal or perpendicular to the vector that is from a point on the line to any other point on the line. Okay, and then let's translate that into this equation into another equation. Well, the normal vector has coordinates a comma b, and that's again generally given, those numbers a and b. And then this vector here is, the way you figured its components out are you do the coordinates of p, which are x and y, and subtract off the coordinates of P0, which are x0 and y0. So it's kind of a little bit backwards. This is, yeah, one convenient thing to remember is that to form the vector P0 to P, it starts at P0, ends at P, it's equal to the vector from the origin to P minus the vector from the origin to P0. Why is it minus here? Well, you can rewrite this, move this over as OP0 plus P0P is equal to OP0. And this equation here is consistent with our way to add vectors, to go from O to P0, followed by, to add this vector, you follow that by P0 to P, and then you get the arrow that starts at O and ends at P. So if you subtract OP0 from both sides, you get this equation here. Okay, so then, all right, once we've explained this part, then we take the dot product, and that's just A times x minus x0, B times the second component here, y minus y0, set that equal to 0, and then doing the algebra, we get that ax plus by plus c equals 0, where c is equal to this thing. On the next page, we'll do an example. Okay, let's find the equation of the line through a point 1, 2, with normal vector -1, 3. And the solution is, well, we know that the normal vector dotted with this vector from P0 to an arbitrary point P on the curve has to equal 0. So the normal vector is -1, 3. The arbitrary point P has coordinates x, y, and P0 has these specific coordinates that we were given. And so the vector from P0 to P, you subtract the components of P from the components of P0 to get this. Then take the dot product, so -1 times x minus 1 plus 3 times y minus 2 equals 0. Do the algebra, and then you get this, and this is the equation. I've made a separate video about how to illustrate this using Sage Math. Let's move on to the case of R3 and a plane in R3 where the story is analogous. So now suppose we're given a point, it will have 3 coordinates, x0, y0, z0, and then again a normal vector. And then we want to find the equation of the plane that passes through this point P0 and is perpendicular or normal or orthogonal to this vector n, which is given by 3 numbers. And once again, the equation is n times n dot P0 to P, where P is the arbitrary point on the plane, and then P0 to P is the vector starting at P0 and going through P. And then their dot product has to equal 0. And once again, I'm translating that. N turns into ABC. P0 to P, you subtract off the components of P, and then you do the subtraction of x minus x0, y minus y0, z minus z0. Multiply then a times x minus x0 plus b times y minus y0, c times z minus z0. Again, that's how the dot product is defined. And then we get either this equation down here, or if you want to distribute the a, b's, and c's, you get this, and where d is some number. So everything here is a variable, it seems, but in practice, a, b, and c are numbers. And so here, a, b, and c are numbers, whereas the real variables are x, y, and z. D is also, in practice, a number because you're given x0, y0, z0. And I've made a Sage Math video showing how to plot 3D plots in Sage.